In the heart of a collapsed star, where gravity has won its final, absolute victory, a fundamental law of reality breaks, not just a little, but completely. Quantum mechanics, the bedrock of our understanding of the small, insists that information can never be destroyed. It can be scrambled, hidden, or rearranged, but the universe, in its very essence, must keep a perfect record. Yet, general relativity, Einstein's masterwork describing the grand dance of spacetime, predicts an object so dense that nothing, not even the information that constitutes a particle, can escape its grasp. This is the black hole information paradox, a chasm that has divided physics for half a century. It's a cosmic riddle that forces us to question the very nature of what is real. The story begins not with a grand discovery, but with a deceptively simple question posed in the early 1970s by a graduate student named Jacob Bekenstein. He wondered, what happens if you drop a hot cup of tea into a black hole? According to the second law of thermodynamics, the total entropy, a measure of disorder, or more precisely, the hidden information within a system, can never decrease. The hot tea has entropy. The black hole, according to classical physics at the time, had none. It was a perfect, simple object described by just three numbers: mass, charge, and spin. When the T crosses the event horizon, its entropy vanishes from our universe. The second law is violated. This was an unacceptable breach in the fabric of physics. Bekenstein proposed a radical solution. What if black holes themselves have entropy? And what if that entropy was proportional not to the black hole's three-dimensional volume, as one would intuitively expect, but to the two-dimensional surface area of its event horizon? This was heresy. It implied that all the complex information of the countless stars, planets, and particles that a black hole had consumed over billions of years wasn't stored within its infinite density, but was somehow smeared across its boundary. Stephen Hawking was famously among the idea's fiercest critics. He set out to disprove Bekenstein by applying the strange rules of quantum mechanics to the curved spacetime around a black hole. He expected to find that Bekenstein's idea was nonsense. Instead, in 1974, he made a discovery that shook the foundations of cosmology. He found that black holes are not truly black. Due to quantum fluctuations at the event horizon, they must radiate a faint thermal glow, now known as Hawking radiation. And because they have a temperature, they must, by the laws of thermodynamics, have entropy. Hawking was right. Hawking's own calculations confirmed the formula. A black hole's entropy is indeed directly proportional to the area of its event horizon. This wasn't just a minor correction, it was a profound clue from the universe about its own operating system. Think about what this means. The information capacity of your computer's hard drive depends on its physical volume. The amount of data you can store in a library depends on the volume of its shelves. In every system we have ever encountered, information scales with volume. But in the most information-dense, gravitationally extreme objects permitted by the laws of physics, this rule is shattered. It's as if the universe's ultimate hard drive stores all its data on the casing, not on the platters inside. This bizarre property led physicists Gerard 't Hooft and Leonard Susskind to formulate one of the most provocative and mind-altering ideas in modern science, the holographic principle. The principle suggests that the information content of any region of space can be fully described by a theory that lives on the boundary of that region. In essence, it proposes that our three-dimensional reality might be a holographic projection of information encoded on a distant two-dimensional surface. Just as a security chip on your credit card contains a tiny flat hologram that projects a three-dimensional image, the entire universe, every galaxy, every star, every atom in your body, could be the 3D projection of a 2D reality. This isn't a metaphor. It's a startling hypothesis born directly from the rigorous mathematics of black hole thermodynamics. The evidence from these cosmic behemoths suggests a maximum information density for any volume, known as the Bekenstein bound. And this bound scales not with the volume, but with its surrounding surface area. If you try to pack too much information into a region, it will exceed its own Bekenstein bound and collapse into a black hole, the universe's way of enforcing its own data storage limit. The paradox of the black hole, an object that seemed to be an information sink, has ironically become our primary source of information about the ultimate structure of reality. It whispers that space-time is not fundamental, that the world we perceive, with its depth and volume, is an emergent, effective description of something far flatter and far stranger. If the most extreme objects in the cosmos are governed by this holographic law, are they the exception or are they the rule? From that paradox emerges a law so powerful it acts as a mathematical bridge between the two pillars of modern physics. If the information of a black hole is stored on its 2D surface, could the information of our entire universe be encoded on some vast cosmic boundary? For decades, this remained a tantalizing but speculative idea. Then, in 1997, a theoretical physicist named Juan Maldacena published a paper that sent shockwaves through the scientific world. He provided the first concrete, mathematically rigorous example of the holographic principle in action. This discovery, known as the anti-de Sitter/conformal field theory correspondence, is our forbidden law, a Rosetta Stone that translates the language of gravity into the language of quantum mechanics. It is, to date, the most successful realization of the holographic universe. To understand its power, we must first visit the theoretical laboratory where it was discovered. The ADS part refers to anti-de Sitter space, a specific type of model universe. Unlike our own universe, which appears to be expanding at an accelerating rate, anti-de Sitter space has a negative curvature. Imagine a saddle shape or one of M.C. Escher's mind-bending tessellations stretching to infinity. It's a universe that curves inward on itself. Within this theoretical bulk of spacetime, gravity exists. There are black holes, particles, and the familiar pull of spacetime curvature. The CFT part refers to conformal field theory, a type of quantum field theory that describes particles and their interactions, but crucially, it does not include gravity. This quantum theory lives on the lower dimensional boundary or edge of the anti-de Sitter space. Maldacena's earth-shattering insight was that these two descriptions are perfectly dual to one another. They are mathematically equivalent. Every single event, every particle, every interaction happening in the five-dimensional gravitational ADS bulk has a perfectly corresponding description in the four-dimensional non-gravitational CFT on the boundary. This is not an approximation. It is a precise one-to-one mapping. A complex gravitational problem in the bulk, like two black holes colliding, can be translated into a much simpler problem about interacting quantum fluids on the boundary. A quantum entanglement on the boundary can be translated into a geometric connection, a wormhole or Einstein-Rosen bridge, in the bulk. This duality is the forbidden law because it directly connects the two previously irreconcilable domains of physics. It shows, in a mathematically unimpeachable way, how a reality with gravity can emerge from a lower dimensional reality without it. The 3D world is the hologram. The 2D boundary is the holographic plate containing all the data. The implications are staggering. It suggests that space-time itself is not fundamental, but emergent. The very fabric of reality, the stage on which everything plays out, could be a construct stitched together from the quantum information living on its periphery. While the ADS/CFT correspondence was formulated in a toy universe, its principles are so profound that physicists are working tirelessly to apply them to our own cosmos. This leads to an even more unsettling concept, that of reality as a cosmic one-bit prison. If all the information in the universe is finite and can be encoded on a 2D surface, it implies that reality has a fundamental resolution. Just as the image on your screen is made of a finite number of pixels, spacetime itself might be made of fundamental, indivisible units of information on the order of the Planck length, the smallest possible distance in physics. Below this scale, the concepts of space and distance may cease to have meaning. Our seemingly smooth, continuous reality would be at its core digital. This isn't just a philosophical musing, it has testable consequences. Experiments like the holocometer at Fermilab were designed to search for a holographic noise, a fundamental jitter in spacetime itself caused by this ultimate pixelation. While no such noise has been detected yet, the very fact that we can design experiments to look for it pulls the holographic principle out of pure theory and into the realm of falsifiable science. If this principle holds true for our universe, it reshapes everything. Our perception of a three-dimensional world would be a profoundly convincing illusion. Every law of physics, every chemical reaction, every neurological impulse that constitutes a thought would be the emergent behavior of bits of information stored on a cosmic boundary. The universe isn't a place containing things, it is the information that describes those things. And we, along with the stars and galaxies, are just incredibly complex patterns written in that cosmic code. The cosmos isn't a stage for a play. The cosmos, the play, projected from a script we are only now beginning to read.